Well, hello again. We are going to talk about the third type of proof required for discrete mathematics, and this is strong induction. Some of you have seen this before in your first year of HL or SL math, but we're going to do it again just to kind of review what's going on. So there are three steps involved in strong induction. The first is you are going to show that the statement is true for some base cases. Okay, and that's usually the case where n equals 1, or maybe even a couple of cases depending on how complicated the thing you're trying to prove actually is. Step 2, you're going to assume that the statement is true for all n's that are less than some arbitrary value k. And then based on that assumption, we are going to show that the statement is true for n equals k. So the best way to do this is with an example. This is a recurrence relation, which we are going to talk about later in the chapter, but we are assuming that there is a sequence of a's, and the 0th term is 2, the first term is 5, and every other term after that is based on the terms that come before it. So the n plus second term is equal to 5 times the n plus first term minus 6 times the nth term. All right, and we are going to show in general that the nth term is actually 2 to the n plus 3 to the n. Okay, so let's do that. So step 1, we're going to show that this is true for n equals 0 and n equals 1, since those are the base cases that we've been given. So I'm simply going to replace all n's with zeros and show that that's true, and then replace all n's with 1s and show that that's true. So when I replace all n's with zeros, I get that the 0th term is 2 to the 0 plus 3 to the 0, which is 1 plus 1, which is 2, and I was given that the 0th term was 2, so I know that this statement is true. And moving on to the first term, I replace all n's with 1s, and I get the first term is 2 to the 1 plus 3 to the 1, which is 2 plus 3, and that's 5. And I was told that the first term was 5, so that's actually true as well. So we've completed step 1. Step 2, we are now going to assume that the nth term is 2 to the n plus 3 to the n for all n less than k. All right, so k minus 1, it's true, k minus 2, it's true, all the way down to the very beginning. Okay, so based on that assumption, we will now show that a to the k is equal to 2 to the k plus 3 to the k. All right, so here's how we do that. This is the definition that we were given, that the kth term is 5 times the k minus first term minus 6 times the k minus second term. And so since k minus 1 is less than k, and k minus 2 is also less than k, then I can use the assumption that I made in step 2 to make a substitution. Okay, I assumed that the k minus first term was equal to 2 to the k minus 1 plus 3 to the k minus 1. So I make that substitution. And I also assumed that the k minus second term was 2 to the k minus 2 plus 3 to the k minus 2. So I make that substitution as well. So now I simply manipulate this so that it looks like that bold statement that I have at the top. So the first thing I do is I distribute the 5 in the first set of parentheses and the negative 6 in the second set of parentheses. And that's what it looks like. And what I notice is that 6 that I've distributed is actually 2 times 3. So what I can do to create higher powers of 2 and 3 is I can write this 6 as 3 times 2, and I can write this 6 as 2 times 3. And that's going to give me an extra 2 to combine with these k minus 2 2's over here, and I have an extra 3 here that I can combine with these k minus 2 3's over here. And if I do that, then this stays the same. This 5 times 2 to the k minus 1 stays the same, and this 5 times 3 to the k minus 1 stays the same. But notice this 2 will combine with this 2 to the k minus 2 to create 2 to the k minus 1. And I still have that extra 3 sitting out in front that wouldn't combine with anything else. I have this extra 3 over here that's going to combine with the k minus 2 3's over here, giving me an exponent that's 1 higher, so that's 3 to the k minus 1, and I've still got that 2 over here that can't combine with the other 3's. Well, now the blue terms are both some constant times 2 to the k minus 1, so I can combine those. And the red terms are some constant times 3 to the k minus 1, so I can combine those. And if I do that, I get 2 times 2 to the k minus 1 if I combine the blue terms, and I get 3 times 3 to the k minus 1 when I combine the red terms. Well, that's an extra 2 for the blue terms and an extra 3 for the red terms, and what happens is I get 2 to the k plus 3 to the k. So I have now proven using strong induction that the kth term is actually 2 to the k plus 3 to the k. We're going to cover more of these proofs when we get into recurrence relations in the next video. But until then, if you have any questions, please let me know, and I will see you tomorrow.